Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 88. It's on Bernoulli's equation. And a great application of this is the reason why docks aren't solid, why they're made of piling so water can flow underneath it. If you were to have a big boat like this, we're looking at it from above, come into a dock, if it was solid, it would force all the water out of the way. And that fluid, as it's moving faster, would have a lower pressure. There'd be a higher pressure on the outside of the boat, which would slam it up against the dock. And so Bernoulli's equation is really conservation of energy inside a fluid. And to solve most of the problems, you'll first have to understand how the continuity equation works. Continuity equation is equal to A1 times V1 equals A2 times V2, where A1 is the cross-sectional area and V1 is going to be the velocity. So if we look at a pipe like this, and so fluid is flowing through it from left to right in two different points, A1 is going to be the cross-sectional area, so the area of this pipe here, and A2 is going to be the area over here. And so if we look at the velocity, that's what V1 stands for. Since we have a large cross-sectional area here, we're going to have a relatively low velocity. And then as we move to the right, since we're decreasing that area, we're going to have a high velocity. And so if you know the velocity at any point in the pipe, since that whole fluid's moving, if you know the cross-sectional area anywhere else, you're going to be able to figure out the velocity there. An application of this, if you've ever had a hose, as water comes out of it, it's got a large cross-sectional area. If you put your thumb in front of it, what are we doing? We're decreasing the cross-sectional area. What happens to the velocity? It increases. Now, if we look at Bernoulli's equation, it's somewhat scary when you see it the first time. It looks like this. And so this is going to be Bernoulli's equation. And it's frightening to look at, but what we've really added here are simply two things. We've added y, which is going to be the height of the pipe, because that's the potential energy. And then the other thing we've added is a rho, which is going to be the density of the fluid, because those can affect the amount of energy that we have. And so if we break apart this equation, we've also got 1 on the left side and 2 on the right side. If we look at this first one, P1 stands for the pressure. So inside the fluid itself, how much is that fluid pushing in on a point inside the fluid itself? So that's going to be the pressure energy. We then have this, rho g y1. Now that seems confusing, but let me kind of write it out a different way. If we were to, instead of write rho or density, if I were to say the mass, this is g, gravitational energy, or gravitational field strength. And then if we were to look at y, if I wrote h there, or the height, what is mgh? You know that. That's just the potential energy of the fluid. And so that second bit of this equation is going to be the potential energy of the fluid. And then if we write this next one, what is 1/2 mv squared? That'd be kinetic energy, but we're writing density since we're dealing with the fluid. So that's going to be the kinetic energy. And so those are the three ways we can get energy on the left side of that pipe. It's the pressure of the fluid, it's the potential energy, how far it is in relation to gravity, and then the last is going to be the speed of that fluid. And since this is the conservation of energy, in these 2 points of the pipe, since we know the energy over here, and we know it's going to be an equal amount of energy over here, we can solve some pretty complex problems. So for example, if we were to look at this pipe right here, on both sides, they both have the same height, or the same y value. So I've taken those out of this equation. And so where's the velocity going to be faster? It's going to be faster on the right side of the pipe. So we're going to have a faster velocity on the right side, slower velocity on the left side. So what has to be our pressure on the right side? Well, to make it equal on either side, conservation of energy, we're going to have a lower pressure. So just like in my example of the ship, if the fluid is moving fast, then it's going to have a lower pressure. And so let's start with the continuity equation, which is simple. We've got a PHET simulation. You can see as the fluid's moving, it's moving faster on the right. And so if we use a flux meter, on the left side, the cross-sectional area is 10 meters squared, and the speed is going to be 0.5 meters per second. So that would be my A1 times my V1. If I move over to the right side, now my cross-sectional area is 1. What's my velocity? 5 meters per second. And so I can just solve for the one I don't know, and I can figure that out. If we were to just change the pipe, now the cross-sectional area is 5 meters squared. What's going to be my speed? It's simply going to be 1 meters per second. And so continuity equation is very, very simple. If we were to apply Bernoulli's equation, what we're really adding to it is the density of the fluid and then the height of the fluid. And so let me give you a thought experiment. Let's say I were to take a half a gallon of milk and I were to pop 3 holes in it and quickly put tape over it like that. So the whole thing is filled up with a fluid, and then I were to simply pull the tape off the side. So what are we going to get? Streams of milk coming out of the carton. But do you think those streams would look like this, or like that? If you were to look at it from the side, which is going to be the correct way the streams are going to come out? Well, the correct answer is C. Why is that? It's because if we look down here at the bottom, this is like the second part of the pipe. So on the left side of the pipe, we have way more potential energy inside the milk, and so that's going to be converted to more kinetic energy, and the stream is going to go out farther. Whereas if we go to the top, it's not going to have as much potential energy above it, and so it's not going to be able to have as much velocity, so it's not going to go out as far. And so understanding both sides of the pipe, where's the potential energy greater, it really helps you understand how Bernoulli's equation works. And so it's written like this. Left side, remember, it's going to be the pressure energy, the potential energy, and then the kinetic energy. And they're going to balance. So it's the conservation of energy. If we know what's on the left side, we can solve kind of what for what's on the right side. So let's try to solve a problem using Bernoulli's equation. So I've got a pipe. I've got a left side and a right side. On the left side, you can see the velocity is lower. I'm giving you the pressure on the left side, but what we're going to solve for is the pressure on the right side. So let's go through this equation. On the left side, I'm giving you the pressure. On the right side, we don't know what that pressure is. On the left side, do we have less or more potential energy in the pipe on the left side than we would on the right side? Well, the density of the fluid, since it's water, is going to be the same on both sides. And since the pipe on the right side is going to have a higher height, it's going to have a higher potential energy on the right side. What about this? Are we going to have a higher kinetic energy on the right side or the left side? Since it's going faster on the right side, our velocity is faster on the right side, it's also going to have a faster kinetic energy or higher kinetic energy on the right side. And since I'm giving you the pressure on the left side as 128, we would expect to have a pressure on the right side that has to be lower since we have higher potential and kinetic energy on the right side of the pipe. So let me show you how I would solve this. I would write it out with the things I know. So the density of the water, since it's the same fluid, is going to be 1,000 kilograms per meter second. And we know the gravitational field strength is 9.8 meters per second squared. On the left side of the pipe, we know the pressure, 129 kilopascals. We know the velocity, and then we also know the height. And on the right side, what we don't know is going to be the pressure. That's the unknown, but on the right side, again, we have a higher height, higher velocity, so we have higher energy right there. Should be a lower pressure. So if I were to write it out, I would write it out like this. Now, I'm not going to include the units because it simply wouldn't fit on the screen. Watch one thing that could screw you up. Since it's 129 kilopascals, I'm writing that out as 129,000 pascals because that's the unit that we're going to use. I then solve it, and so this right here is going to be my potential energy left side, kinetic energy left side. If we compare that to potential and kinetic on the right side, you can see on the right side both those values are greater. But we're simply solving for pressure too, and so using significant digits, I'm getting around 90 kilopascals on the right side. And that's because I'm limited by this. It's not a very precise measurement in the velocity. So let's test that and see if that comes out. On the right side, it's around 87 kilopascals. So it's around 90 kilopascals. And so we can use Bernoulli's equation not only to calculate, but we can use it to just analyze confusing situations when we have a fluid. So how does a curveball work? When you throw a curveball, it should drop. So as the pitcher tries to, or as the batter tries to hit it, it's going to drop right at the end. And so how does that work? How does a curveball work using the fluid of air? So as you throw a ball, let's say it's not spinning. As it's moving through the air, the fluid of the air is going to move around it. But since it's not spinning, the velocity on the top and the bottom is going to be exactly the same. But when you throw a curveball, you start spinning it. So it's spinning like this, and it generates a wind on the top, which counteracts the wind that's already coming in, and so it decreases the speed of the wind on the top. But on the bottom, since the wind over the ball and now the wind generated by the spin of the ball are both going in the same direction, the fluid on the bottom is going to be going faster. So Bernoulli's equation, what happens to our pressure if the fluid's going faster? Pressure is going to decrease. Since we have lower pressure on the bottom, there's going to be a force pushing it down. So that's how a curveball curves. And so did you learn to construct an explanation of Bernoulli's equation using the conservation of energy? Remember, on the equation, left side equals right side. Could you use it to make some calculations and solve some problems in a moving fluid? And then finally, could you use it to show where the pressure changes? So in a dock, in a curveball, or in any fluid? I hope so, and I hope that was helpful.